In the next several videos, we're going to be looking at examples to get a feel for how to use the equations from the previous videos. As always, I would encourage you to pause the video and try to work the problem, or at least set up the problem, and then come back to the video and see how to work it as a solution. So in this example, we're going to split it into several parts, one part for each problem. But for all of these parts, we're given a point P, -2, 6, and 3, and a vector A, which is equal to y in our x direction, plus the quantity of x plus z in our y direction. So before we get into looking at exactly what we're trying to find, let's look at our given information a little closer. So first, our point P, which is -2, 6, and 3. So right away, I can say that this is a Cartesian point. The reason I can say that is because none of our three quantities there are an angle. So remember, for our cylindrical, we have rho, phi, and z. So of course we would expect to have an angle, so typically reported in degrees, but maybe it'd be radians for that middle term. And then for our spherical, of course, we have r, theta, and phi. So we have two angles here. But because we have only we don't have any degrees or any indication that any of these units are radians, we can know that we are dealing with Cartesian. So now with our vector A, in previous examples in our first unit, we were dealing with uniform fields. And that meant that we had constant values being multiplied by our unit vectors. But now we have these variables, so we see we have some spatial dependence on our vector field here. So things are getting a little bit more complicated in terms of that. Okay, so just a couple things to sort of point out about our problem statement. So now let's get into the first part of our problem. We want to express this point P in both cylindrical and spherical coordinates. So let's come down here to the next page and work this first part of the problem. So express P in cylindrical and spherical coordinates. So what we're doing with both of these is we're going to be doing a point-to-point transformation. Two point-to-point transformations, really. So let's first look at finding our P in cylindrical coordinates. So we're just going to use the equations that we talked about in the previous video. So, or not the previous video, but a previous video. So we know rho is equal to the square root of x squared plus y squared. So substituting in our values of x and y, we know x is -2 and our y is 6. So plugging in and evaluating, we get roughly 6.32. Next, for our phi, we had that phi is equal to the inverse tangent of y divided by x. So plugging in, we have inverse tangent of 6 divided by -2. So now you want to be careful plugging this into the calculator, because if you're working from an older calculator, for instance a TI-83 or TI-84, what that's going to tell you is it's going to say that this is equal to -71.565 degrees, which is incorrect. So instead of doing that, what you want to do is sort of consider what this looks like in our xy plane. So just real briefly, if we are sort of looking top down and we have our xy plane here, so we're sort of going back to 2 dimensions, our rho is going to be the distance from the origin, and our phi is still going to be the distance or the angle up from this x-axis. So in this case, we have a -2 for x and a 6 for y. Sorry, so we have -2 for x and 6 for y. So we're somewhere here. So we would expect, of course, our rho to be positive, so that's this distance here, and we would expect our angle, phi, to be something a little above 90. Of course, the -71 that I had written before isn't correct. What that's actually given us is an angle here that's 180 degrees off. So it's given us -71 because it's using 6, -2. So it's, or sorry, rather 2, -6. So 2 in x, -6 in y. So it's moved this negative sign and it's associated it with this term in the numerator. So basically to fix that, all we need to do is add 180 and we get an angle of 108.43 roughly. And so again, all that aside over here was just to say be careful when you're plugging in these inverse tangents in your calculator. So finally, we can just say our z is the same in both rectangular, Cartesian, and cylindrical. So we can say z is equal to 3. So then we can say our point in cylindrical coordinates, so I'll put P sub cy, is 6.32, 108.43 degrees, and 3. So that would be our point in cylindrical coordinates. So now we want to do another point-to-point transformation to get our spherical. We could do it from this cylindrical data, but we have a couple of approximate values here, and also maybe we messed up a calculation. So I would always recommend going back to our given information if it's not substantially more work. So in this case, we're going to go from Cartesian to spherical then. So r is equal to the square root of x squared plus y squared plus z squared. Plugging in our values, we have -2 for x, 6 for y, and 3 for z, and that ends up being 7 exactly. Next, we have our theta, which we defined as the inverse tangent of, in the numerator, we have square root of x squared plus y squared divided by z. So plugging in, we have inverse tangent, clean that up a little bit, so we have inverse tangent of the square root of 40, so I've gone ahead and sort of combined those couple terms there, divided by our z, which is 3, and we get that that is approximately 64.62 degrees. And then finally, for our phi, it's going to be the same as we had above for our cylindrical, but let's just go ahead and write it. So we have inverse tangent of y divided by x, which is equal to, as we saw above, 108, approximately 108.43 degrees. So then our point in spherical coordinates, P sub SPH, is 7, 64.62, and 108.43 degrees. So that's how we would do our point-to-point transforms. And of course, we could confirm by doing a point-to-point transform one way or the other between these two, and we should get roughly the same thing, particularly if we're using stored values for these approximate angles or magnitudes.